dear viewers, the title of my lecture is Approximate Solution of an Initial Value Problem. So far the differential equations considered by us had a general solution. In the case of an initial value problem, we obtained a unique solution by using the initial condition y at x naught equal to y naught in the general solution. This is just one of the three possibilities that might occur in the general case. In the general case, an initial value problem dy by dx equal to f x y, where y x naught equal to y naught may have no solution, precisely one solution, or more than one solution. For example, let us consider the initial value problem mod of y dash plus mod of y equal to 0, where y at 0 is given to be equal to 1. Now, this differential equation mod of y dash plus mod of y equal to 0 has only one solution, that is y equal to 0, because the left hand side of this differential equation is the sum of two non-negative real valued functions. So, their sum is 0, means y is equal to 0 for all x, but this does not satisfy the initial condition, because the initial condition is y at x equal to 0 is 1. So, this initial value problem does not have any solution. Next, let us consider the initial value problem dy by dx equal to x, where we are given that y at x equal to 0 is 1. Now, this differential equation dy by dx equal to x we can solve by using the method of separation of variables. We may write it as dy equal to x dx, then integrate both sides, we will have y equal to half of x square plus c. Using the initial condition y at x equal to 0 is equal to 1, we get the value of the constant c as 1, and so this initial value problem has only one solution, which is y equal to half of x square plus 1. If we consider the initial value problem x y dash equal to y minus 1, where we are given y 0 equal to 1, then we can see that it has infinitely many solutions. You see, if you take x equal to 0, then y is equal to 1 follows from the differential equation x y dash equal to y minus 1 directly. So, let us take x not equal to 0, divide by x this differential equation, and then write dy by dx equal to y by x minus 1 by x. We can write it as a linear differential equation of first order, and then find it the integrating factor. It will turn out that the integrating factor here is 1 by x. We can multiply this equation by the integrating factor 1 by x and integrate with respect to x. We shall see that the solution is y equal to 1 plus c x for all x not equal to 0, but y equal to 1 plus c x also satisfies the condition y 0 equal to 1. So, we can say that y equal to 1 plus c x is the solution of the given initial value problem for all values of x, where c is an arbitrary constant. Now, since c is an arbitrary constant, so the given initial value problem has infinitely many solutions, and thus there arise the following two fundamental questions. Existence of a solution: under what conditions does an initial value problem of the form 1, that is dy by dx equal to f x y, y at x naught equal to y naught have at least one solution. Number 2, uniqueness of the solution: under what conditions does the initial value problem have an unique solution. Now, the theorems that answers these two questions, that is existence of a solution and uniqueness of solution, are known as existence and uniqueness theorems. The examples considered by us above of the initial value problems were so simple that we could find the answers to the existence and uniqueness of the solutions just by looking at them or just by doing some simple calculations, but in the case of complicated differential equations, that is the ones which cannot be solved by the elementary methods studied by us so far, the existence and uniqueness theorems which we are going to study now will be of great practical importance. Let us look at the existence theorem first. If f x y is continuous at all points x y in some rectangle R of the x y plane given by mod of x minus x naught less than a, mod of y minus y naught less than b, and bounded in R, that is to say mod of f x y is less than or equal to k for all x y in R. You can see in this picture, this is the region R in the x y plane bounded by x equal to x naught minus a and x equal to x naught plus a, and y equal to y naught minus b and y equal to y naught plus b. Then the initial value problem has at least one solution by x, and this solution is defined at least for all values of x in the interval mod of x minus x naught less than alpha, where alpha is the minimum of a and b by k. So, that is to say we can say that if the function f x y in the initial value problem is continuous in some region of the x y plane containing the point x naught y naught, then the initial value problem has at least one solution. So, let us now talk about the uniqueness of the solution. The uniqueness theorem gives us the conditions, the sufficient conditions which f x y has to satisfy in order to that the initial value problem has precisely one solution. So, if f x y and its first order partial derivative with respect to y, that is delta f over delta y, are continuous for all x y in some rectangle R, that is mod of x minus x naught less than a, mod of y minus y naught less than b, and bounded in R, that is to say mod of f x y less than or equal to k and mod of delta f over delta y less than or equal to m for all x y in R, then the initial value problem dy by dx equal to f x y, where y x naught equal to y naught has at most one solution y x. Now, in view of the existence theorem, that is theorem number 1, it follows that the initial value problem will then have precisely one solution. This solution is defined at least for all x in the interval mod of x minus x naught less than alpha, where alpha is the minimum of a and b by k. The uniqueness solution of the unique solution of the initial value problem can be obtained by using the Picard's iteration method, which we shall study a little later. Now, since dy by dx is equal to f x y, so mod of f x y less than or equal to k implies that mod of dy by dx is less than or equal to k. That is to say that the slope of any solution curve y x in the region R is at least minus k and at most plus k, and hence a solution curve passing through the point P, that is x naught y naught, will lie in the region R bounded by the lines through P having slopes minus k and plus k. Now, depending on the form of the region R, there arise two cases. In the case 1, when a is less than or equal to b by k, we will have alpha is equal to a, because alpha is the minimum of a and b by k. So, when alpha is equal to a, in this figure you can see that this is your solution curve. The solution curve lies in the region R bounded by these two lines having slopes k and minus k. L2 has slope k while L1 has minus k, and they both pass through the point x naught y naught. The solution curve also passes through the point x naught y naught. So, here when alpha is equal to a, the solution exists for all values of x in the interval x naught minus a to x naught plus a, and its slope is at least minus k and at most plus k, as because it lies in the region shaded region, which is bounded by the two lines having slopes minus k and plus k. In the case 2, when a is greater than b by k, alpha being the minimum of a and b by k will imply that alpha is equal to b by k. So, here mod of x minus x naught less than alpha means the solution curve lies in the region shaded region which is from x naught minus alpha to x naught plus alpha, that is x naught minus b by k to x naught plus b by k, and the slope of the solution curve is at least minus k and at most plus k. L1 has slope minus k while L2 has slope plus k, and the solution curve is passing through the point x naught y naught. Now, let us study remark 1. The condition 2, that is mod of delta f over delta y less than or equal to 1 for all x y in R in the uniqueness theorem can be replaced by the Beaker condition mod of f x by 2 minus f x by 1 less than or equal to m dash into mod of by 2 minus by 1, where x by 2 and x by 1 are any 2 points belonging to the region R. Now, this condition 3 is known as ellipsis condition. Now, if a function f x y is such that mod of delta f over delta y is less than or equal to m, then it will always satisfy the ellipsis condition, because by the mean value theorem we can write that mod of f x by 2 minus f x by 1 is less than or equal to some constant m dash times mod of by 2 minus by 1. So, thus we arrive at a stronger form of the uniqueness theorem, because there are many functions which do not possess a continuous partial derivative, but satisfy the ellipsis condition for some constant m dash. Let us study remark 2. If the function f x y is continuous, it is not sufficient to guarantee the uniqueness of the solution. For example, let us consider dy by dx equal to 3 times y to the power 2 by 3, where we are given that y at x equal to 0 is 0, and the region R is given by mod of x less than 1, mod of y less than 1. We can see here that f x y, which is equal to 3 times y to the power 2 by 3, is continuous in the given region R, and by 1 x equal to x cube and by 2 x equal to 0 are two different solutions of the differential equation for all values of x in R. Thus, the differential equation dy by dx equal to 3 times y to the power 2 by 3 does not have a unique solution, and this is because the function f x y, which is 3 times y to the power 2 by 3, does not satisfy the ellipsis condition in the region R, since f 0 y minus f 0 0, which will be equal to 3 times y to the power 2 by 3 divided by y minus 0 will be equal to 3 over y to the power 1 by 3, which is unbounded in every neighborhood of the origin, and origin is a point which lies in the region R. Therefore, the function f x y does not satisfy the ellipsis condition. Now, let us study the Picard's iteration method to obtain a unique solution of the initial value problem. This method gives us a sequence of approximate solutions of the initial value problem, one which converges to the unique solution by x of 1 by the Picard's theorem, which we shall state later on. The practical value of the Picard's method is limited because it involves integrations which may be complicated to obtain. We note that by integration the initial value problem dy by dx equal to f x y, where y at x naught is y naught, may be written as y x equal to y naught plus integral x naught to x f t y t dt. Now, here the variable t in the integrand has been used because x occurs as an upper limit of the integral here. Since the unknown function y t occurs in the integrand on the right side of equation 5, equation 5 is known as an integral equation. Then a first approximation by 1 to the solution y x is given by y 1 x equal to y naught plus integral x naught to x f t y naught t dt. So, the unknown function y t in the equation 5 on the right hand side in the integrand is replaced by the known value of y, that is y naught, and we determine the first approximation y 1 x to the solution y(x) of the initial value problem. Second approximation y2 is then obtained from y2x equal to y0 plus integral x0 to x f t by 1t dt. So, we use the value of y1x to determine the next approximation y2x, and so on we continue. The nth approximation yn is then given by ynx equal to y0 plus integral x0 to x f t by n minus t dt. In this way, we will obtain a sequence of approximations by 1x, by 2x, by 3x and so on, by nx and so on, which converges to the solution y(x) of the initial value problem 1 in view of the following theorem of Picard. Picard's theorem states that under the conditions of theorems 1 and 2, the sequence 7 by 1x, by 2x, by nx and so on of functions y n x given by equation 6 converges to the solution y(x) of the initial value problem. Let us solve an initial value problem using Picard's method. We are given dy by dx equal to 1 plus y square, where y at x equal to 0 is 0. So, if you compare this differential equation y dash equal to 1 plus y square with the standard form dy by dx equal to f x y, you find that f x y is equal to 1 plus y square. The initial condition y at 0 equal to 0 gives us x naught equal to 0 and y naught equal to 0, and hence f t y naught, the value of f t y naught is equal to 1 plus is equal to 1. Therefore, by 1 x is equal to y naught plus integral x naught to x f t y naught dt, which will be equal to integral 0 to x 1 into dt, and after integration we then have y 1 x equal to x. So, first approximation to the solution of the dy by dx equal to 1 plus y square, where y 0 equal to 0 is x. The next solution, next approximation by 2 x is equal to y naught plus integral x naught to x f t by 1 t dt. By 1 t is equal to t. So, f t by 1 t will be equal to 1 plus t square, and therefore, by 2 x is the integral of 0 to x 1 plus t square dt, which will give us x plus x cube by 3. So, second approximation to the solution by x of the initial value problem is x plus x cube by 3. Next we find y 3 x, by 3 x is then y naught plus integral x naught to x f t by 2 t dt. Making use of the value of y 2 t as t plus t cube by 3, we have y 3 x as integral 0 to x 1 plus t plus t cube by 3 whole square dt. After integration we get the value of the third approximation by 3 x as x plus x cube by 3 plus 2 by 15 x to the power 5 plus 1 by 63 x to the power 7, etc. If we find the exact solution of our initial value problem, it turns out that the exact solution of our initial value problem is y equal to 10 x. See, our initial value problem is dy over dx equal to 1 plus y square. So, we can use the method of separation of variables and write the differential equation as dy over 1 plus y square equal to dx, integrate and use the initial condition y at 0 equal to 0. We can see that y equal to 10 x is the exact solution of our problem, and we know that the Maclaurin series expansion of 10 x is x plus x cube by 3 plus 2 by 15 x to the power 5 plus 17 by 315 x to the power 7 and so on, which is valid in the region mod of x less than pi by 2, that is the series converges in the interval minus pi by 2 less than x less than pi by 2. Now, if we compare our y 3 x, the third approximation y 3 x with the series that occurs in 9, we find that first 3 terms of y 3 x and the series in 9 are the same. The series in 9 converges for mod of x less than pi by 2, and so we may expect that our sequence of approximations by 1 by 2 and so on converges to a function which is the solution of our problem for mod of x less than pi by 2. These are the approximate solutions of our initial value problem. By 1 x is equal to x. So, we have this curve by 1 x equal to x, by 2 x is equal to x plus x cube by 3, and then we have the curve for by 3 x. So, these are approximate solutions of our initial value problem, which converge to the exact solution by equal to 10 x of our initial value problem. Picard's method can be extended to simultaneous equations and equations of higher order. Let us first discuss Picard's method for simultaneous differential equations of first order. Let us consider the two differential equations of first order, dy by dx equal to f x by z and dz by dx equal to g x by z. Next, we discuss Picard's method for second order differential equations. Let us consider the second order differential equation d square y over dx square equal to f x y dy by dx with the initial conditions y at x naught equal to y naught and dy by dx at x naught equal to z naught. Now, if we put dy by dx equal to z, then the second order differential equation d square y over dx square equal to f x y dy by dx gives rise to two first order simultaneous differential equations. They are dy by dx equal to z and dz by dx equal to f x by z. The initial conditions will be y at x naught equal to y naught and dy by dx at x naught equal to z naught gives us then dz at x naught equal to z naught. Now, this system of simultaneous differential equations of first order now can be solved as by the method which we have done explained earlier. Let us take an example on this method. Let us use Picard's method to find an approximate value of y at x equal to 0.1, where we are given that y double dash plus 2 x y dash plus y is equal to 0 and y at x equal to 0 is 0.5, y dash at x equal to 0 is 0.1. So, let us now discuss the solution of this problem. Let us take dy by dx equal to z, so that d square y over dx square is equal to dz by dx, and thus the given equation reduces to dz by dx plus 2 x z plus y equal to 0, where y at x equal to 0 is 0.5 and z at x equal to 0 is equal to 0.1, and thus we have the problem to solve dy by dx equal to z and dz by dx equal to minus of 2 x z plus y with the initial conditions y naught equal to 0.5, z naught equal to 0.1 at x naught equal to 0. Now, by the Picard's theorem, we have y equal to y naught plus integral x naught to x f x by z dx, which is equal to 0.5 plus integral 0 to x z dx. f x y z is equal to z here, and z is equal to z naught plus integral x naught to x g x by z dx. Z naught is equal to 0.1 minus integral 0 to x 2 x z plus y, because the value of g x by z is minus of 2 x z plus y dx. And the first approximations to y and z are then given by y1 equal to 0.5 plus integral 0 to x z naught dx. We replace z by z naught here, which is equal to 0.5 plus integral 0 to x. The value of z naught is 0.1, so 0.1 dx. This will give you y1 equal to 0.5 plus 0.1 into x, and z1 will be equal to 0.1 minus integral 0 to x 2 x z plus y will become 2 x z naught plus y naught dx. So, this will be equal to 0.1 minus integral 0 to x 0.2 into x, because z naught is 0.1. So, 0.2 into x, y naught is 0.5. So, we have the integral of 0.2 into x plus 0.5 dx, and after integration we will get the value of z1 as 0.1 minus 0.5 into x minus 0.1 into x square. Second approximations are by 2 equal to 0.5 plus integral 0 to x z1 dx, which is equal to 0.5 plus integral 0 to x. The value of z1 came out to be 0.1 minus 0.5 x minus 0.1 x square into dx, which is equal to 0.5 plus 0.1 into x minus 0.5 into x square by 2 minus 0.1 into x cube by 3. Z2 is equal to 0.1 minus integral 0 to x 2x z1 plus y1 dx, substituting the value of z1 and the value of y1, and integration, after integration we shall have the value of z2 as 0.1 minus 0.5 into x minus 0.3 into x square by 2 plus x cube by 3 plus 0.2 into x to the power 4 by 4. Similarly, we can find third approximations by 3 and by z3. By 3 is equal to 0.5 integral 0 to x z2 dx, substituting the value of z2 and integrating with respect to x, we will give us the value of by 3 as 0.5 plus 0.1 x minus 0.5 x square by 2 minus 0.1 x cube by 2 plus x to the power 4 by 12 plus 0.1 x to the power 5 by 10, and z3 as 0.1 minus integral 0 to x 2x z2 plus by 2 dx. Substituting the values of z2 and by 2 here, we will get after integration 0.1 minus 0.5 into x minus 0.3 x square by 2 plus 2.5 x cube by 6 plus 1 by 12 x to the power 4 minus 2 x to the power 5 by 15 minus 0.1 x to the power 6 by 6, and hence at x equal to 0.1 the values of by 1, by 2 and by 3 are: by 1 is 0.51, by 2 is 0.50746667, by 3 is 0.50745933, and thus by at 0.1 is equal to 0.5075, correct up to 4 decimal places. Now, we will discuss some numerical methods to find an approximate solution of an initial value problem. The differential equations that occur in the practical problems are so complicated that the methods which we have discussed earlier may not be applied to them, or they are, even if we find solutions of those differential equations by the known methods or the elementary methods, the formulae are so complicated that one often prefers to find a numerical solution of the differential equation. So, we will be discussing the two methods, numerical methods for finding an approximate solution of the given initial value problem. We shall assume that the initial value problem has an unique solution in an interval containing the point x naught. Let dy by dx be equal to f x by at x naught equal to y naught. The methods that we are going to discuss, that is Euler's method and the improved Euler's method, are known as step by step methods. We start with an initial value of y, that is y naught at x equal to x naught, and then find an approximate value of y, that is by 1 at x equal to x naught plus h, that is x 1. In the second step, we find an approximate value of y, that is by 2 at x equal to x 2, which is x naught plus 2 h. H is the step size, and at each step we use the same formula to determine an approximate value of y. So, these methods are called step by step methods. Let us say y equal to g x be the solution of this initial value problem in some interval containing x naught, and let us say x 1, x 2, x n be equidistant values of x in this neighborhood. Let us take x I equal to x naught plus I h. So, these values are equally spaced with this step size h. Then in this method we approximate the curve of solution of the initial value problem by a polygon whose first side is tangent to the curve at x equal to x naught. By the Taylor series, y at x plus h is equal to y x plus h by dash x plus h square by 2 factorial by double dash x plus and so on, which can be written as by x plus h into f x y, because dy by dx is equal to f x y, and so we have h into f x y plus h square by 2 factorial d square by over dx square, that is by double dash x, it becomes d over dx of f x y and so on. Now, when h is the step size h is small, we can neglect the terms containing h square and higher powers of h, and we thus get an approximate value of y at x plus h as by x plus h f x y. So, using this approximate formulae, we then compute the first approximate value of y at x naught plus h, that is x 1. We compute the approximate value y 1 y by y naught plus h f x naught y naught, which approximates y at x 1, that is y at x naught plus h. Next, we compute y at x naught plus 2 h, that is we compute y 2 from y 1 plus h f x 1 y 1, which approximate y at x 2, that is y at x 1 plus h, or you can say y at x naught plus 2 h. Now, this is geometrical interpretation of this method. You can see here that this is solution curve of the given initial value problem. At the point x naught, okay, at the point x naught y naught, this is the tangent to the curve whose slope is given by f x naught y naught. We have dy by dx equal to f x y. So, the slope of the tangent is at x naught is f x naught y naught, and this is your step size h. At the point x equal to x naught plus h, that is x 1, the value of y 1 is given by this y 1, and the actual value of y at x equal to x 1 is this one. So, there is an error here. This is the error at the first stage, y at x naught plus h minus y 1, that is the error here. And then in the next step x 2, we then continue along the straight line, okay, which passes through the point x 1 y 1 and has slope f x 1 y 1. So, then when we compute y 2 from y 1 plus h times f x 1 y 1, this is our y 2, while the actual value of y at x equal to x 2 is this. So, there is an error here. This is the error in the next stage. Continuing in this manner, we then obtain y n equal to y n minus 1 plus h f x n minus 1 by n minus 1, where n is equal to 1, 2, 3 and so on. This is called Euler method or Euler-Cauchy method. Now, in the Taylor series which occurs in 10, we consider only the constant term and the term containing the first power of h, because we have neglected all the terms which contain h square and higher powers of h. So, this method is called a first order method. The error in this method is quite significant unless h is small. Since we have neglected all terms containing h square and higher powers of h, the truncation error in this method is at each step is of order capital order h square. Now, in addition to this truncation error, there are round off errors as well in this method, which may affect the accuracy of the values by 1, by 2, by 3 and so on. The practical value of the Euler's method is limited, but due to its simplicity, it is helpful for understanding the basic idea of the improved Euler's method, which we shall be discussing now. Let us before we discuss improved Euler's method, let us take an example on Euler's method. Say, let us solve dy by dx equal to x plus y, where y 0 equal to 0 for 0 less than or equal to x less than or equal to 0.8 by taking h equal to 0.2 and h equal to 0.4, using Euler's formula method, and let us compare the results. For h equal to 0.2, we have the formula, Euler's formula, y n plus 1 equal to y n plus 0.2 into x n plus y n, that is the value of f x n y n. f x y here is x plus y. So, f x n y n is x n plus y n. Now, if you write this ordinary differential equation as a dy by dx minus y equal to x, you can see that this is the first order linear differential equation, and we can then find its integrating factor and multiply this by the integrating factor and integrate with respect to x. It follows that y equal to e to the power x minus x minus 1 is the exact solution of this problem, making use of the initial condition by 0 equal to 0. Now, here we have tabulated the values of by 1, by 2, by 3, by 4 for x equal to 0.2, 0.4, 0.6, 0.8 when we take h equal to 0.2, and then we have also tabulated the values of y for x equal to 0.4 and 0.8 where we have taken h to be 0.4, and then we have compared the errors in the two cases. Now, you can see that when n is 0, that is we have x naught 0.0, y naught is equal to 0.00, and the value of 0.2 into x n plus y n is this, and then we get using the Euler's formula the value of y at x equal to 0.2 as 0.000. Next we calculate 0.2 into x 1 plus y 1, which is 0.040. We then get the value of y 2, that is y at 0.4 as 0.040. Similarly, by 3, that is y at 0.6 we get as 0.128, and y at 0.8 we get as 0.274. And when we calculate the exact values of y from the exact solution of the initial value problem, y equal to e to the power x minus 1, we see that y at x equal to 0 is given by 0.000, y at 0.2 is 0.021, y at 0.4 is 0.092, y at 0.6 is 0.222, and y at 0.8 is 0.426. These are the errors which occur when we compute the values of y by using the Euler's formula, taking h equal to 0.2. So, at x equal to 0, the error is 0. At x equal to 0.2, the error between the approximate value and the actual value is 0.021. The error in by 2 is 0.052. The error in by 3 is 0.094. The error in by 4 is 0.152. And when we take h equal to 0.4, we see that y at 0.4 comes out to be 0, while y at 0.8 comes out to be 0.160. These are the values of y which we have found for y at 0.4 from the table 2. Y at 0.4 is 0.040 and y at 0.8 is 0.274, and the errors, the difference between the two values of y here is, here the value of y at 0.4 is 0, here it is 0.040. So, the difference is 0.040, and here the difference in the values of y is 0.274 minus 0.160, that is 0.114. Now, since the error is equal to capital order h square in this method, changing the step size from h equal h to 2h implies that the error is multiplied by 2 square, that is 4. See, here we have taken first h is equal to 0.2 and then we have taken h is equal to 0.4. So, we have changed the step size from h to 2h. Now, changing the step size from h to 2h means that the error is multiplied by 2 square, that is 4, but since when we take the step size 2h, we need only half of the steps that we have to take when we take the step size as h. The error will only be multiplied by 4 by 2, that is 2, and hence comparing the corresponding approximations with the step sizes h equal to 0.2 and 2h equal to 0.4, we find that they differ by 0.04 for x equal to 0.4 and 0.114 for x equal to 0.8, while the errors in y2 and y4 actually are 0.052 and 0.152, and thus we see that the approximate solution gets better and better, that is closer to the exact solution as we reduce the size of h, but the process is not very rapid, and hence we study a modification of this method known as improved Euler's method. Now, if we take more terms in the Taylor series in the equation number 10 into account, it leads us to numerical methods of higher order and precision, but the computation of f dash and f double dash becomes complicated. So, our aim is now to avoid their computations and replace it by computing f for a suitably chosen auxiliary value of x y. The method is called as improved Euler method or improved Euler-Cauchy method. Sometimes it is also called as Heinz method. So, now let us study improved Euler's method. In this method, at each step first we compute the auxiliary value by n plus 1 star equal to by n plus h f x n by n, and then we determine the new value of y, that is by n plus 1 by the formula by n plus h by 2 into f x n by n plus f x n plus 1 by n plus 1 star. Now, let us study geometrical interpretation of this method. In the interval x n to x n plus half h, the solution curve is approximated by the straight line through x n by n whose slope is f x n by n, and then we continue along the straight line with slope f x n plus 1 by n plus 1 star in the interval x n plus half h to x n plus h. You can see that in this formula by n plus 1 equal to by n plus h by 2 into f x n by n plus f x n plus 1 by n plus 1 star, we can break it into two parts, by n plus h by 2 f x n by n. So, that is the value which we get by taking the straight line through x n by n whose slope is f x n by n in the interval x n to x n plus half h. At x n plus half h, the value of y will be from this straight line will come out to be by n plus h by 2 f x n by n, and then we continue along the straight line whose slope is f x n plus by n plus 1 star in the interval x n plus half h to x n plus 1, and that will give us the value of by n plus 1. Let us see this figure for n equal to 0. This is the solution curve of the initial value problem, and this is the point x naught y naught. This is the tangent to the curve at the point x naught y naught, because the slope of the tangent to the curve at the point x naught y naught is dy by dx at x equal to x naught, which is f x naught y naught. So, in the interval x naught to x naught plus h by 2, we get the value of by 1 star from here, this is by 1 star, and then we continue along the straight line, this one whose slope is f x 1 by 1 star in the interval x naught plus h by 2 to x naught plus h, that is x 1, and then at x equal to x 1, this gives us the value of y, that is by 1. So, there is an error, this error is there, this error is the error in the improved Euler's method in computing the value of y at x equal to x naught plus h. In this method, the equation by n plus 1 star equal to by n plus h f x n by n is called the predictor, while the equation by n plus 1 equal to by n plus h by 2 into f x n by n plus f x n plus 1 by n plus 1 star is called the corrector of by n plus 1. So, it is called a predictor corrector method. Let us consider an example on this method. Using improved Euler's method, solve dy by dx equal to x plus y, y 0 equal to 0 for 0 less than or equal to x less than or equal to 1 by taking h equal to 0.2. Taking h equal to 0.2, we will have by n plus 1 star equal to by n plus 0.2 x n plus y n. Here f x y is x plus y, so f x n y n is x n plus y n, and by n plus 1 will be by n plus h by 2, that is 0.2 by 2, f x n by n, that is x n plus y n, f x n plus 1 by n plus 1 star, that is x n plus 1 plus by n plus 1 star, and then we have by n plus 0.1, and then x n by n plus 1 star is by n plus 0.2 x n plus y n. So, we put that value here and we see that we have 1.2 into x n plus y n and then x n plus 1 plus y n. X n plus 1 is x n plus h, that is x n plus 0.2. So, we get by n plus 1 as by n plus 0.22 into x n plus y n plus 0.02. This table gives us the values of y corresponding to the values of x with the step size h equal to 0.2. When n is 0, x naught is 0, y naught is 0, and we compute the value of 0.22 x naught plus y naught plus 0.02 as 0.0200. We then get the value of y at x equal to 0.2 as 0.0200. Y at 0.4 comes out to be 0.0884, y at 0.6 comes out to be 0.2158, y at 0.8 comes out to be 0.4153, and y at 1.0 comes out to be 0.7027. The actual values of y are 0, 0.0214, 0.0918, 0.2221, 0.4255, 0.7183. The error that occurs in computing the values of y using this method are 0 here, this is 0.014, 0.0034, 0.0063, 0.0102, 0.0156. So, you can see from the error that occurs here in computing the values of y that this method is better than the Euler's method that we have discussed earlier. Now, let us discuss the error in this method. The local error in the improved Euler's method is of order h cube. To prove this, let us say f n cap is equal to f x n by at x n. If we use the Taylor's expansion, we will find that by at x n plus h minus by at x n is equal to h into f n cap. This is f n cap because h into dy by dx at x n is f at x n by x n. So, we will have f n cap here plus half h square f n dash cap plus 1 by 6 h cube f n double dash cap and so on, approximating the expression in the brackets in by f n plus 1 equal to y n plus h by 2 f x n by n plus f x n plus 1 by n plus 1 star. If we approximate this expression inside the brackets by f n cap plus f n plus 1 cap and again use the Taylor's expansion, we find that by n plus 1 minus by n is approximately half of h plus half of h into f n cap plus f n plus 1 cap, and when we use Taylor's expansion here we will get half h f n plus f n cap plus h f n dash plus half h square f n double dash cap and so on, which will be equal to h f n cap plus half h square f n dash cap plus 1 by 4 h cube f n double dash cap and so on. Now, if we subtract this equation 12 from the equation 11, we will get the error as h cube by 6 plus into f n double dash cap minus h cube by 4 f n double dash cap and so on, which is equal to minus h cube by 12 f n double dash cap and so on. So, since this is the error here is of the order of h to the power 3. Now, we have x n equal to x naught plus n h, and thus the number of steps over the interval x naught to x n, which is n, is proportional to 1 by h, and therefore, the global error in this method is of order h cube by h, that is h square, and so the improved Euler's method is called a second order method. Now, in our lecture today we have discussed the numerical solution of an initial value problem. We discussed two methods here, Euler's method, improved Euler's method. In our next lecture we shall discuss power series method for finding the solution of a homogeneous differential equation, and then we will discuss the particular cases there, that of Legender's equation and the Wessel's equation. That is all. Thank you.